Alright, let's continue on with this special relativity here, and we're going to do something called time dilation. And so let's explain this first with a thought experiment. This was Einstein's thought experiment. So in the last video we talked about how the speed of light was a constant, that no matter what anybody did or how they were moving, this was always what the speed of light was. It was invariant. We couldn't change it. It didn't vary from coordinate system to coordinate system. Everybody that ever measured the speed of light always came up with this value. So let's pretend we have a person standing next to the railroad tracks, okay? Standing here next to it, and then they have a little stopwatch, and then there's a train going by them, right? Big old train. Okay, and I'm going to make up some numbers here. We're going to make this train a bit ridiculously large, but we'll have another person on the train, right? So this is our train. Above this person's head is a mirror, right? However high up this ceiling is. And I think I need to make this ceiling a little higher here, just so that I have some room to draw this. So let's put the ceiling up a little higher here, okay? So they're in a train. There's a mirror on the ceiling above them, and they have a laser pointer. And so what they're going to do is they're going to fire this laser, and they're going to time it. And this laser is going to go up, and it's going to hit that mirror, and then it's going to bounce, reflect back down. And they're going to time it. And let's say that this ceiling is so high that it takes 1 second for the laser light to reach the mirror and another second for it to come back down. Now, if they have themselves a handy-dandy little stopwatch, and they look at their stopwatch, what they would read would be 1 second passed by as the light went on its way up, and 1 second on the way back down, and their stopwatch would read 2 seconds. Okay, so as far as they could tell, this is their little timing clock. This is how they time everything. 2 seconds went by. But now, let's look at it from the perspective of the guy who's on the side of the road watching this train go by. Because remember, this train has a velocity. All right, this train has some velocity v, and we're going to say it's really high. It's near the speed of light. And so when he sees this laser go, he sees this laser not go straight up and straight down, because as it's first fired, the car keeps moving right. So as the car moves right and this laser light goes up, it goes at an angle. And by the time it reaches the ceiling, the little mirror has moved over, and it bounces off the mirror now at this location and hits that mirror and then bounces back down. Okay? And if you think about this, you have to remember this is a longer path. This up at an angle, down at an angle is a longer path than the straight up and straight down. And at first you're like, well, that's no big deal. Of course, that's what you'd see. We would have seen that before. But if you remember that both the person on the train and the person off the train are going to measure the speed of light to be exactly this. And this guy saw light travel in a shorter distance and came up with 2 seconds. And let's say the train was going at such a speed that this distance here was 1.5 seconds for the light to go up and 1.5 seconds to go back down. Like if it was just going at that right speed that made it do that, then the guy on the tracks not moving would have looked at his stopwatch while he timed the light, and he would have gotten 3 seconds for the exact same event. And this disagreement is what is known as time dilation. It states basically that an object moving very fast will have its time slow down. And so the person on the train is moving very fast, and their time slows down, so that when they measure the speed of light, all their clocks, everything, all their counting is all going slower. So they end up getting the exact same result as someone who is sitting still relative to their motion. And the person sitting still relative to motion is going faster. Or I'm sorry, their time is going faster. So they would see 3 seconds, and you have this disconnection between them. This can actually be calculated either geometrically, which is done in your book. You can make this into a right triangle and fill in the sides, and you can look there for that. Or you can calculate it from the Lorentz transformations of how much this would actually be based on how fast the person who was moving was going. So let's take a look at that. Let's write out our Lorentz equations again, our Lorentz transformations. They were x prime equals gamma times x minus vt, and then the only other one we were really too interested in, we're just doing two-dimensional or one-dimensional motion here, is time, which is no longer invariant because we have this gamma factor. This doesn't just go time equals time like in the Galilean ones. It was gamma equals t minus vx over c squared. Okay, so let's take a look at this. What would be a change in time? So from the person on the train, he would measure delta t prime, and delta t prime would be t prime 2, so let's say that's when it returns, minus t prime 1. That would be the time that it was initially shot up. So this would be 0 seconds up in 2 seconds. That would be what it would be at the start of the situation and then at the end of it. So however long we timed it. And if we replace these primes with the Lorentz transformation versions, we get gamma times t2 minus vx over c squared minus gamma times t1 minus vx over c squared. Okay? If we distribute these gammas in, gamma t2 minus gamma vx over c squared minus gamma t1, now negative negative plus gamma vx over c squared. And if we do that, we have a positive gamma vx over c squared and a negative gamma vx over c squared. So they cancel. And what we're left with is gamma t2 minus gamma t1. And if we factor that gamma out, it's just gamma times t2 minus t1, which ultimately just equals gamma times delta t. And so there we have it. This is our time dilation equation. And what this shows you is that the amount of time that would change between these two systems is simply equal to the time in one of them equal to gamma times the time in the other coordinate system. So which way do you do it? Which is the prime, which is the unprime? Well, pretty much what we have to do is figure out the definition of two things. The first thing is called proper time. This will help you use this equation. Because you look at it and you're like, well, wait, is t prime the moving one or is t the moving one? Because if I went through and derived this out with delta t, I could come up with a very similar result. So how do you know which one this is? Well, what you have to do is define proper time. And proper time is the amount of time, in the observers, the guy making all these observations, and the observers, the guy who's doing the one single observer's frame of reference. So proper time is the time from whoever's perspective you're looking at. If whoever's perspective you're looking from, in this case, our perspective is the guy on the side of the track, so his 3 seconds would be the proper time, and this over here of the guy on the train who he's watching him go by, the guy on the train, he would be the dilated time, and that would be the time not. It's the time measured for somebody in relative motion, so not in the inertia, not in the observer's frame. So this is the time for a moving reference frame. And I mean moving reference frame. Moving relative to our observer's reference frame. Basically, this is our reference frame, whatever we're looking at. So if I look at it from his perspective, this is what we get, and the proper time is always going to be your longest amount of time because everybody else is moving relative to it. So the proper time always has to be greater than the dilated time. Okay? The dilated time. So whatever you get here, you need to make sure that your proper time is going to be bigger than that. So you'll always be able to figure out where you should put this because if you go through the values for gamma, remember gamma equaled, put this over here, gamma equaled 1 over the square root of 1 minus v squared over c squared. Well, you look at this and you say, all right, what is this value? So this value is v squared over c squared. Now this number, assuming v is not 0, can basically range from, well, if v is 0, this becomes just the square root of 1, 1 over the 1. So gamma is, so if we do a graph like this, gamma as a function of velocity, well, at v equals 0, gamma equals 1. And then as gamma gets bigger, right, v keeps getting bigger and bigger and bigger and bigger, then this number in the denominator gets smaller and smaller and smaller, and if our value in the denominator gets smaller and smaller, then our actual value gets bigger and bigger. So gamma starts to increase until it reaches the value of c. If we do c squared here, if the speed is c, then you get c squared over c squared. That's 1 minus 1. That's a 0 in the denominator, and it becomes undefined. So out here, at v is equal to c, you end up with an asymptote that you cannot get to. You've ever probably heard, say, you can't go faster than the speed of light. Well, yep, this is, oops, that's not good looking. This is what they're talking about. That these Lorentz transformations with this gamma factor here, it lets you approach the speed of light c, but you can't get to it because it becomes undefined. And if you go over c, if you could somehow skip the speed of light and go to something greater than c, then you end up taking the square root of a negative number and it becomes imaginary out here. And so our values of gamma only range through here, and they're greater than 1. So when I look at this, I know this is a greater than 1 value, and the way I wrote this now, this delta t is smaller than delta t prime, making this the proper time in this situation, and this the dilated time in this section. So you just always have to make sure that it's the gamma is multiplying onto the smaller time, because gamma is greater than 1. It'll raise its value up to a bigger value, which would then be the proper time. Okay? You have to be pretty careful about this. Now, there's one more thing. I want to think about this same exact situation again, but I want to reverse which is the proper time and which is the dilated time. Now, before, we assumed the guy on the side of the track was sitting still, and the other one was the person on the train was the moving reference frame. So our observer was from the guy on the side of the track's point of view. But let's change that around. Let's have the same situation, but this time up, we're going to be observing it from the train's perspective. And in the train's perspective, the train is sitting still. And so he says, all right, I'm sitting still, and I have my little laser light, and there's a little mirror above me, or whatever, right? Or actually, he doesn't even have it. Let's say, everything's the same. Let's say he can have his little laser light. That's fine. But what we're interested in is we're also going to give a little laser light to our guy on the side of the road. So now he has one, and we're redoing the same situation, or the same situation's going on, except he pulls out his laser, and he's got a mirror above him as well, right? So way up here. And the guy on the train says, I'm sitting still, and the person standing on the side of the tracks is moving in that direction at some velocity v. And so the guy standing still, he fires his laser. And just like for the guy on the train before, he sees it go up and down, and he gets 2 seconds. 1 second up and 1 second down. So he gets a time of 2 seconds, right? 2 seconds. But now, from the guy on the train's perspective, what does he see? He sees the laser light go up as the guy, oops, that's not a very good one. I can't undo it here, sorry. That was at a bad angle. Try that again. He said, so he sees this laser light go up, right? Hit the mirror over here and bounce back down. And so he sees the path of this light now being a longer distance, and he now gets a value of 3 seconds or something like that, right? We set this up such that it was a second up and down for him, but 1.5 for the other guy. It's a longer distance at the same speed. So he now gets 3 seconds because now this is the proper time. And so I think you're wondering, well, wait a second, how can we have both of these things occur? Because imagine if we did this exact situation and we gave them both lasers and they were both observing each other, then this guy would see his go up and he'd see it go down, and the other guy would have seen that same situation as before. And so the guy on the train says, I had 3 seconds go by during this event. He had just 2 seconds. And the guy on the side of the road says, no, 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 no. I had 3 seconds go by. I should probably do that in a different color. I had 3 seconds go by. You only had 2 seconds go by. So which one of them is correct? And the answer is a little trickier than this. And we'll really cover the answer a little better when we start doing what are called space-time diagrams. But for the moment, they're both right. And the only way for one of them to be wrong is for something to change, because special relativity only talks about inertial frames of reference, which means frames of reference where there's no accelerations. And as long as these two guys keep going off their separate ways, they can't ever actually get back together and discuss, have a conversation about how much time had gone by. And if they try sending radio signals out to each other because they're getting further and further apart, there would be a delay as we would, because they're traveling near the speed. There'd be a big delay in the radio signals that are traveling at the speed light getting to each other, and by the time it got to each other, you'd end up with the same exact result. And so this leads us to the last little thing, is something called the twin paradox. So you can imagine that we had a pair of identical twins, and one twin stayed behind on Earth, right? And the other twin got in this rocket ship and blasted off into space near the speed of light. V near C, okay? Now, the twin, from his perspective staying on Earth, says, I saw my twin on this rocket ship. Yep, standing on the outside of it. I saw my twin fly away really fast, which means his time is going to slow down. My proper time will stay fast, and I, as he continues on and on, say, for example, if I have an entire month pass, he has only had half a month pass, whatever it would be. We'd have to work it out from the equation above. But let's say he's going fast enough that it cuts his time totally in half. And now I am half a month older than my identical twin. And if I let a year go by, I will be 6 months older than my identical twin. Okay? But if we look at it from the perspective of the twin on the rocket, he says, no, 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 no. I was sitting still, and my brother on Earth sped away from me in the other direction at near the speed of light, right? And I am the older twin. His time is dilated. He is slow. He is slowed down. His time is slow. I am 6 months older than him after a year, not the other way around. Well, who's correct? Well, how about this? Let's set it up so that every month the twin on Earth sends out a radio signal. Just sends out a thing that says, hey, 1 month passed. And so he sends out his first signal, and the twin on the rocket gets the signal when he's here. 1 month. And now the twins, he synchronizes his clock, he resets his stopwatch to 0, and some time goes by. A month later, this twin sends out the next signal that, hey, a month has gone by. Now, the first time he sent a signal out, the signal only had to travel whatever this distance is here, not very far. It only had to travel this distance here to reach this twin for him to get the signal. But it's a month later. So the second twin on the rocket ship is further away now. And so he is way out here now. And the second signal of month number 2 gets sent out, right? So we had our first signal, it was seen here, that's 1 month. Now the next signal, sent out 1 month later from the Earth perspective, takes longer to get there. So from the twin on the rocket ship, he got the first signal a month later, but it's going to take longer for him to get the second signal because he's further away now. So by the time this signal reaches him, he says, okay, for me, 2 months have gone by, yet I've only received word from my twin back on Earth that 1 month has passed, right? So this was 1 month, and this was the second month, right? So between the first month and the second month, the guy on Earth says, hey, he's sent out his signals. The twin on the spaceship says, hey, there's been 2 months of time, and I've only gotten the first month and second month signal. So between the first and second month signal, my twin has only aged a month, yet I have aged 2 months. And if we reverse that, we could do the same thing. This twin could send a signal out saying, hey, here was the first month. And then when he's way out here, after a month, probably a little closer here, he sends out the second signal, which is further away and takes longer to get to this twin. So this twin says, all right, I got the first month. Now I'm going to wait for the second month to get here. And he, instead of waiting 1 month for the next month signal to get there, he has to wait 2 months. So now he says, in that last month for my twin, I aged 2 months, he aged 1 month. And the answer to this is actually that they're both right. And there's no way for either one of them to be wrong sending signals back and forth because of these delays. The only way for one of them to be wrong is for these two guys to get back together and compare. So you could imagine if this twin hopped in a rocket and started going that way, what would happen is, in order for him to catch up to his twin, he'd have to go faster than his twin was going. And if he goes even faster, then his time is going to slow down even more. He's going to start running into all these 1 month signals that his twin had sent out, and he'll start collecting them even faster in less time than 1 month. This is almost like Doppler shifting, right? So if he starts moving towards the source, it becomes a higher frequency, which means he gets the month signals faster than that. So suddenly he starts seeing his twin's time as going faster than his own. And so if he were to go and catch up to his twin, he would find out that he was actually the younger twin, and the twin that stayed on the rocket ship is the older twin now. And conversely, if they had done the opposite, if this twin on the rocket had stopped, turned around, and headed back, he would start running into his twin signals faster than once every month. And by the time he would reach back, he would realize that no, he was the younger twin, and his brother that stayed there was the older one. So essentially, the one that's going to be correct is the one that stays put, that doesn't go to the other one. So if this guy goes back to Earth, he's the younger twin. If this twin goes and catches up to him, then this twin will be the younger twin. Okay? Spend some time thinking about that. It's kind of a hard idea to explain. Again, think of it in terms of Doppler effect. So every so often we send out those little beacons and they just keep getting spread out. And so if you're getting those signals, it seems like they're spread out further than the actual time that has passed, and you think that the other person has their time slowed down, and then vice versa. And then, of course, you can imagine if you got in a rocket ship and started speeding off through space, you'd start running into those little time markers faster and faster than you would, faster than they were sent out. So instead of them being a month apart, they'd only be like 2 weeks apart or something like that, something less than a month. And you would start thinking that your twin was going to be older than you. Okay? I think that's about it for time dilation. The next video we'll do length contraction.